Hi, I'm Tim Yardley. I'm an Associate Director here at the Information Trust Institute, and I'm here today to talk about federated simulations, how we've used them to enable, explore, and realize experimental environments. So this work is in collaboration with Jeremy Jones, Kate Davis, Richard Makwan, and Prosper Panapabi, who have come together under TCIPG to help realize this effort. So we're going to start by framing it a bit. Let's start with what is federation. So federation really is bringing together distributed resources of various different types to accomplish a particular goal. So why do people want to do that? Well, in this particular sector, in the power grid domain, these resources are scarce. So TCIPG is lucky to have an extensive testbed environment with over $6.5 million worth of hardware and software, but not everyone has those resources. So as such, it's difficult to enter into this space. Further though, it's even more difficult to understand how these systems are composed and how to use them. Over the past 10 years, TCIPG has built an incredible knowledge base, putting these systems together in ways that the manufacturers intended and putting them together in ways that are pushing the envelope of original intent to accomplish particular research. So today, how federation is done is people really look at federation from a cyber data point of view. They try to take cyber means, cyber communications, and just pipe it around because a communication pipe is a communication pipe. They haven't really focused on the physical aspects. So here today we're going to work on that. So why hasn't federation been accomplished? Well, fundamentally, the systems in this domain aren't designed to do it. CyberPhysical systems are difficult to compose in that way, and physical systems in the power grid are intended to be physically coupled. That's what they are. They're cyber-physical systems. Further, cyber is easy to federate. It's easy to put a pipe somewhere and direct it to another location. Physical, where they're physically wired, you have to then abstract that out and digitize it in some way, communicate it across, and then recompose it. And that's a bit more difficult. It's harder to do. So we have some proposed solutions for that, and we'll talk about those today. So let's start by looking at the cyber-physical model. So the cyber-physical model in this case is of the Western interconnect is what we're looking at. And to remind you of what happens in these cyber-physical models, you have continuous physics equations that are going on. You have discrete computation and communication, and you have the spatial distribution of systems that are connected and disconnected depending on how you look at the cyber or the physical means. So as you start looking at these large-scale problems like the Western interconnect, and you want to look at it from a federation point of view, you have to distribute these out. In order to distribute out a large model, what do? You break it into smaller models. So in this case, you'll end up with, say, for example, three continuous submodels, and you may run those in 3 different locations. But how do you couple those together? So that's where this framework comes in. So we've created this federated testbed configuration framework that allows us to start linking things together. So as you start linking things together, you can start reasoning about the models between the systems. So obviously computation, what was done previously, was just simply reasoning in the cyber means about the cyber communications in a discrete model form. So they tried to connect these continuous submodels just talking cyber. But you need more than that. So you have to bring in the continuous model coordination and you have to bring in the discrete model coordination as you start reasoning about these systems. And that's where this glue starts coming into play. Once you have this, you can start also doing cyber and physical event injection, and we'll talk more about that in a second. So with our goals, what did we set out to do for this? We wanted to develop a framework, right? We wanted to lower the barrier to entry, to be able to realize research in this space and to realize it in both a distributed and federated way, as well as in a localized way. We needed to solve some engineering problems in order to do that. How do you link these systems up in a way that allows you to reason about them? And then we also wanted to empower the science problems. So linking them up just isn't enough. You also have to do some special work in between to actually deal with the cyber to physical conversions and mappings across the system, locking time steps and various other aspects. And then once you do this, it makes sense to have an open repository for this. We want to create a repository where people can store these experimental operations, store these systems, and share them amongst each other so that you can create a community around this. The last part, well, we created the framework, so we need to actually use the framework, right? So we wanted to link different simulations together with that framework. So this builds on some prior work from Illinois. You've seen us talk about, and you can see us talk about our automation for the RTDS, where we're programmatically controlling a single simulator. We've publicly released that, and it's available and in use at a couple institutions already. And then there's also the federation that's been done in the past. So the ability to send just the cyber data back and forth. We've done that with the Deter framework, and we've done that with just VPNs from point to point between various different locations and test beds. All of those have limitations, though. So we're trying to build on that. So I've talked a lot about power and about cyber physical systems, but what about cybersecurity? So the real motivation for this is to focus on the ability to inject, the ability to manipulate, the ability to reason about these systems when faced with cybersecurity concerns, when faced with things like data injection, when faced with things like attackers trying to do nefarious things to the system. How do you make the systems more trustworthy, robust, and resilient? This allows us to do that. So linking these physical models provides the ability to do data injection and manipulation and to look at the physical impact. We can observe and modify the relationships between components. And the most important thing is we can do this in an automated and programmatic way. We can reason about the system and move forward, linking different components together in ways that perhaps weren't originally intended. So in order to realize this, there's certain steps that we have to take. First, we have to split the model into multiple pieces. In this case, we've split the model into two pieces, a power network and a generator. We have to then federate those two separate systems. We have to explore the coupling between those systems, bounding our problems, looking at the limitations both of our framework and of the simulations themselves. Then we introduce interactions. We take control actions, for instance, and we do that by writing some code and then calling those functions. And then we experiment. We see what we can do, how it works, how it behaves, etc. So we're going to talk about that today. So today we have the Western Interconnect that's modeled. On the left-hand side here, we're modeling this in a 9-bus simplified system. In the yellow is a single generator, and in the pink is basically the representation of the right-hand side here in the pink as well. So if you look at the full model on the right-hand side, we've split, as I said, the generator, which is on the left, and the power network on the right. The generator model is visualized here as well. So the yellow on this screen represents the same yellow on the other side. And the pink is collapsed in the generator model to basically a single line. So the generator model doesn't know the rest of the power network. It's just getting information from that. And how does it get that? Well, the information from the generation simulation and the power network simulation are passing back and forth between the two entities, and they're passing through our code in the middle. And the code in the middle is representing, takes the data that's being passed and forth in a JSON representation, JavaScript object notation, and then operates on it in between with those actions and experimental operations that I've mentioned before. So we're going to actually show a demo here. We're going to start it out with just synchronizing the two instances. So we're going to start both simulators up, and the simulators are passing the information in between. So what you'll see here in the middle is you'll see information flowing back and forth and the messages being correlated. You'll see that the windows of the generators, the generation here is saying 163 megawatts. The generation on this side is also saying 163 megawatts. They're in sync. They're operating as if they're normal. So now we're going to start introducing some instability. So what we're first going to do is open up a single breaker at bus 7. And when we do that, you're going to see the generator on this side respond and cause actions. And then you'll see correspondingly this side synchronize and cause actions on its side as well. The generators will then, after a short while, come back into sync. So as you can see, they're basically both back at 163 megawatts at this point. And the messages have been passing in between from these two. There's no direct connection between these two simulators. They're running on two completely different machines that could be located anywhere in the nation or the world. So as we go through that, what we're going to do now is we're going to close that line. We'll again see the system respond on the right-hand side, and correspondingly the actions on the right-hand side, the generator is responding accordingly. And we're back to normal with the system state, coming back to steady state. So steady state is great and interesting, but what happens if an attacker starts to attack in between? So the first thing we're going to do is we're going to introduce this concept of data injection. So what we're going to do in data injection is we're going to take the value that's currently snapshotted when we start the injection, and we're going to just replay that value across, no matter what happens on the right-hand side. So now we're going to do that same action as before. We're going to open up the line again on breaker 7. So we open up the breaker on 7, and you see the data going back and forth, but you don't see a response on the generation side anymore. There's no response there. And the reason why there's no response there is that we're sending the prior value as if nothing changed, the steady state value, despite the fact that the system is trying to send the real value. Our code in between is replaying the old value. So we're going to turn off that injection, and we're going to reclose that line, and you'll see that the generator here immediately starts responding, and the generator on this side then responds and comes back into synchronization with the others. They'll come back to steady state right around 163 megawatts as they go through this. So you can see that you can introduce both dynamics and steady state aspects. So these are running in a runtime environment of PowerWorld's software called PowerWorld Dynamic Studio, and that'll be available soon. But this instrumentation, this glue, will all be open sourced. So one of the things that you can't do with PowerWorld is you can't programmatically control things like fault injections. You can only program those in. So now we're going to introduce a 3-phase fault, and we're going to do that with our code by talking to the back end of the system. So we're going to introduce that 3-phase fault here at bus 7. And as we introduce that fault, the system will trip off the generator effectively here. It'll drop to 0 megawatts, and then you'll see instantly on this side the response on the same way. So that generator has come to 0. It's not off, but it's generating 0. So it's still spinning, still generating power, but it's being dumped to ground. The rest of the network isn't being served. Okay? So we're going to remove that fault now. And when we remove that fault, you'll see again, the generator over here immediately starts responding, coming back, and this generation load starts coming back as well, serving the loads that are now being served again from the 3-phase fault being removed. So takeaways from this: federation of the underlying physical model is actually possible. We're not just sending bits on the wire. We're not just focusing on the discrete models. Currently, you can federate the same simulators and reason about the limitations of both the framework that's integrating them and the simulators themselves. And we're extending and adding new support and new plugins and new operations that you can take on this. In the future, very, very soon, we're going to be releasing all of this to the public, and we're going to be able to begin to deal with the time synchronization between the two entities. Now, why that's important is you can only, at the moment, link 2 different simulators that are running in the same time stepping and of the same type. But we're going to as soon as we get synchronization in there, we're going to be able to link the simulators together. Now, you may have noticed that in the simulation before, there was a slight lag. And the reason for that is we have to run one simulator about 1.5 seconds ahead of the other to communicate back in time to the other one to link it up. So there's a slight delay there. When we get time synchronization, we'll be able to pause the simulators and synchronize their time so that they operate in lockstep, closing that gap down. That support will then also be used to link in RTDS and other simulators like MATLAB Simulink and SimPower and other aspects to talk to the system just regardless of the fidelity or the steppings that they operate. And obviously, we're going to be extending support and adding even more plugins as we move forward. So I want to thank you for listening to our demo, and have a good day.